Okay, we are starting module essentially 3.2, and we're going to be talking about weak acids and bases, which are calculated pH very differently from strong acids and bases because of the fact that they don't completely dissociate. So, what is a weak acid? We have talked about this before. It's essentially it only partially ionizes or partially dissociates. Okay, so weak acid partially ionizes, which means it's going to be an equilibrium instead of a straightforward arrow. Okay, so a weak acid, this is actually important. Some people associate a weak acid with something that's not very concentrated, and that's not true. You could have a very concentrated weak acid, like a 2 molar acetic acid. So weak does not mean not concentrated, does not mean not concentrated. Okay, it just means that's the type of acid that it is. Okay, so if you look at this little picture that I have over here, if you have strong acid, we know it completely turns into H plus and A minus, which is why we can calculate the pH from the H plus. However, since a weak acid only partially turns into H plus and A minus, and this is actually a good representation because most of it does stay together, that's what's going to affect the pH, only the amount that dissociates, which is why we have to do an ice table to figure out that H plus. Okay, examples that we will use a lot are any of those, any acid that is not one of those 6 strong acids you have to have memorized. What I use a lot of the time is acetic acid, so the acetate ion C2H3O2, so HC2H3O2, phosphoric acid H3PO4, any of those, again, that are not of the 6 strong acids, okay? I am going to give you a relative acid strength handout. This is really just so that we don't have to look up all of the K values or the Ka values of these weak acids. You're going to have this sheet right there, so make sure you print that one off as well. Okay, so this is just like regular equilibrium, it's just with acids. So we're going to be writing the equilibrium constant for a weak acid. So what does a weak acid do when it's dissolved in water? That's what the equation that we're going to use for the equilibrium constant is. So essentially the acid equation is HA, so it could be whatever acid. Obviously it has an H on it, and remember we only move one H at a time, so it really doesn't matter, plus water makes equilibrium arrow. It's going to act like an acid, so it's going to donate an H plus, so it's going to make H0 plus and A minus aqueous. Okay, so this is our generic acid equation. So if I ask you to write the acid equation, or you're calculating Ka or anything having to do with it acting like an acid, this is the equation that you want to write. Okay, so if I looked at this, I'd be like, well, for this Ka, so we're going to use a little subscript A for acid, B for base. Now, still the same K, products over reactants. So it would be H3O plus times A minus. Now remember, you can just use H plus if you want to, over my reactants, which are just HA, because H2O is a liquid and will not affect concentrations. Okay, so that's how we calculate Ka. All right, so if I'm to set up an ice table, which will be very similar, I'm going to write my equation, HA plus water makes H3O plus A minus I C E Okay, we're going to use one, say I have 1 molar of my acid. So 1, we don't care about the water because it's liquid, it doesn't actually affect anything, so you can ignore that column. I would start with none of my products, like a generic ice table. This will be minus X plus X plus X. So this is 1 minus X, X, and X. So that means that my Ka would look like this, X times X over 1 minus X. Now, the good thing for acids and bases is we're only ever going to be moving 1 hydrogen at a time. So we're not going to have like minus 2X or anything squared. It's going to be nice and easy like this. It's going to be X and whatever minus X. Okay. Now, this means if you look at this equation, if my stuff at the beginning is not the same, we're going to have to end up using the quadratic equation. So I do actually have a workaround for the quadratic equation. Okay, so essentially these usually look quadratic, but, so I'm actually gonna put that in here, usually look quadratic, but Okay, if Ka is really small, which it will be since these are weak acids, but if Ka is very small, okay, so like times 10 to the negative, 10th or something like that, you can actually drop that change in X. And I'll tell you why here in a minute. And drop the minus X. Or in other situations, if you've got a plus X. But we'll use those situations later. Okay, so what I'm talking about is this right here. You can actually drop that part. So it would be just X times X over your initial concentration, which in my case is 1. Okay, now why can you do that? Well, if Ka is really small, if you go through the calculations, the amount that your HA is going to change is not very much. Again, look up here. Remember, most of it stays together. So this is not going to change very much, and it's actually going to change in such a small amount that significant figure-wise, it's not going to matter. Now, it will matter what these concentrations are because you can't just have 0. But this change is not going to matter. So you can actually drop it. Now, when I say very small, there is technically a rule. But anytime I give you a problem like this, especially on the exam, you're going to be able to drop that minus X. Okay. The rule is it's okay to drop if X is less than 5% of your starting molarity. Okay, so that's the rule for being able to drop X. You can check it after the fact. I know you have to actually go through the calculation before you check that the X was okay to drop. I'm not going to make you check because, like I said, most of the time, the problems I'm going to give you, you will be able to drop the X. Okay, so Ka is really small. X is going to be minimal in regards to what I started with. You do still have to calculate for X, but you can drop that minus X. All right, so there are actually 3 types of problems that I could ask you regarding weak acids, okay? So first of all, I could just say, what is the pH of blah, 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 weak acid? And you can't just use the concentration because, again, only some of them dissociate. So in order to do that, you are going to have to use an ice table. Now, what you get from the ice table, if you look up here, we've finished with our concentration of HA, our H3O plus, and our A minus. And what is pH based on? H3O plus. So if you have that X value, then you can calculate pH. So ice will give us this at equilibrium, and then you can easily find the pH, right? Negative log of whatever that X value was, okay? Again, you have to do the ice table if it is a weak acid. Otherwise, you will not get the correct answer. All right, we can also, I could say find the Ka for an acid if I tell you what the pH was of it, okay? So in this case, if you have pH, you can always find the H3O plus or the H plus concentration, right? 10 to the negative pH. Now, once you have that, then I can plug it into my Ka, right? Because if I know this X value, I actually know both of these values, unless I added something weird in, because they're going to be the same because it's a 1-to-1 ratio. So you can actually plug those in and then pretty easily find Ka. Now, I am going to go through some examples of these, so give me just a sec. And then the other thing I could ask you is like, how much did it ionize? What is the percent ionization of this? And if you remember back to equilibrium, percent ionization is how much this changed by, right? If I started with 1 molar and it lost minus X, that's the percent that dissociated, or the percent that essentially broke down. So what it's looking for is X, right? Whatever that X was. Now, in other cases, if it was a 2X, it was looking for the 2X. But again, these are always going to be 1-to-1. So finding percent ionization, essentially, we're looking for that minus X, whatever it lost, that X is the ionized amount. Ionized amount. Now, if I want the percent, right, you're going to have to do the amount lost, which is just X, over the starting concentration, because I want the percent, right, times 100. Okay, so the amount lost is X. X would go up top over your starting concentration times 100. That is how you would calculate the percent ionized in a test. So like I said, we're going to go through some examples of these. I'm actually going to pause this video and do the examples in a separate one, so maybe you can come back and do them later.